So, dear students, welcome to another lecture of digital control systems. In this lecture, we will discuss about state feedback controller. Generally, when we design controllers, we use the transfer function of the given system. However, a state feedback controller is designed uh, through the state variable method. That means we need to have the state space model of the given system, and then by using the state space model we can design a state feedback controller, right? Now, what is a state feedback controller? So let us discuss this one. Let us consider a single input single output system which is given by equation 1. This is the state space model of a single input single output system. Now, in state feedback design, we feedback the states of the system to the input, and the purpose is that we can place the closed loop poles of the given system at desired locations. Now, the state feedback controller has two problems which we will discuss, which are associated with state feedback controller. The first one is the regulation problem, and the second one is the tracking problem. Now, regulation problem, what is regulation problem? When we want that the state of the system should approach zero from any initial state. For example, okay, so if the state of the system is anywhere and it approaches to some equilibrium point, right? It approaches to some equilibrium point. So this problem is known as regulation problem, where we actually study the internal stability of the system. That is, the regulation problem is is associated with the internal stability of the system, and by bringing the state of the system from any arbitrary initial state to zero, we actually are achieving the internal stability of the system, right? Then second problem, now in this, the control law that is used is uk minus k into xk. So this is, let us say, some equation number 2. Now then we have tracking problem. Now in tracking problem, the output, the response of the system is tracked in reference to the reference signal, right? Or with respect to the reference signal. Okay. So if the reference signal is, let us say, like it is a step input, so the output is tracked. Okay. Or you can say if the reference signal is changing with time, so the response is, you know should also change, right? So this problem is known as the tracking problem, and the control law, the control algorithm that is used for this problem is given by this equation, where rk here is the reference signal. Now, first of all, we will discuss the state feedback controller design using pole placement technique for regulation problem, right? So if we substitute the control law that is given by equation 2, and the control law given by equation 2 is uk is equal to minus kxk, and if we put this in equation number 1, that is x k plus 1 is equal to axk plus buk, right? So if we substitute this uk here, so we will get xk plus 1 is equal to axk minus bkxk, right? So this will give us this equation here, right? Okay. So now we can design this case such that the eigenvalues of this matrix, right, they lie within the unit circle, because we are dealing with the discrete systems. So we do the stability analysis of a discrete system in Z domain, and we want that the closed loop poles of the given system should be located within the unit circle, right? So if this k can make the eigenvalues of this closed loop equation to place in the within the unit circle, we can say that the problem of regulation is solved. This means that we will be able to bring the states of the system from any arbitrary value or initial state to the zero, right? So we can define the control problem for state feedback controller as that we have to design a state feedback gain matrix K such that the control law given by UK is equal to minus KXK can place the poles of the closed loop system this in the desired locations, right? So this is the statement or control problem that we have defined, and we would be working on this control problem, and our purpose is to obtain the state feedback gain matrix K. Now there is a necessary and sufficient condition for this, and the necessary and sufficient condition for this is that the pair AB, so pair AB is from the state equation, right? Okay, so it must be controllable, right? And the second second thing is that because all the states of the system are fed back to the input side, so we assume that all states are measurable. So if we see the block diagram of this, so this is a delay element. It has input xk plus 1, and the output here is xk, and we will feedback this xk, the state, by multiplying this with some matrix A to the input side, right? Here we are adding this with B matrix, and the input is UK, right? So we can see that it is fed back to the input side. The states are fed back to the input side, right? So if we are feeding the states back to the input side, so it means we are assuming that all states are measurable. Now, let us design K, the state feedback gain matrix. This is state feedback gain matrix by transforming the state model into the controllable canonical form. The first of all, because we want that our AB pair, it should be controllable. So we will first transform the state model, because every state model is not controllable, right? So we will transform the state model to some controllable canonical form, and then we will obtain the state feedback gain matrix, right? Now the characteristic polynomial of the given system is given by this equation. This is the characteristic polynomial, wherein a1, a2, a3, all these are the coefficients of z, right? And this is your state matrix. This is the state matrix, right? Now, if we take some controllability matrix, now controllability matrix UC is given by, as we all know, it is given by B, then AB, then A square B dot 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 A n minus 1 B. So this is the controllability matrix. For a given system to be controllable, this matrix should have full rank. The rank of this matrix should be full, that is n. Okay, so it should be the order of the system, right? Now, first of all, we'll take a controllability matrix. We will consider a transformation matrix T, and this transformation matrix is given by the equation UC into W, where W is a weight matrix. This is the weight matrix which is given by this equation, right? So we have all these coefficients of Z. Okay, so you can see here we have the coefficients of the the characteristic polynomial here. So all these AIs means all these coefficients are the coefficients of the characteristic polynomial. All these elements of matrix W, the weight matrix, are the coefficients of the characteristic polynomial, right? Now let us assume a new state. Now let us assume a new state, and this new state is this new state vector, sorry, and new state vector is x bar, such that it is related with the actual state vector. This is the actual state vector, and this is the assumed state vector, right? So we have used the transformation matrix. So we can say that x bar is equal to t inverse x, right? Okay, so this x bar is the controllable form, uh, controllable state vector, you can say. So we are using the transformation matrix to transform the actual state vector to the controllable form, and hence this will transform the given system by equation 1, and equation 1 is xk plus 1 is equal to axk plus buk, and yk is equal to cxk, right? So this will be transformed to controllable canonical form, right? And the new state equation will be, this is the new state equation, right? Which is controllable, right? So that means this pair A bar and B bar, okay, this pair is controllable, right? This is controllable. Now uh, this A bar and B bar are given by these equations, right? Because uh, these are the controllable matrices. So our actual matrices will also be controllable. This pair will also be controllable, right? Now let us find out. Okay, so now if we find out, so now because we have a new state model which is xk plus 1 bar is equal to A bar x bar k and plus B bar uk. So we have a new state model here, right? And this pair A bar and B bar is this is controllable, right? This is controllable pair. So now we will first find out. So let us assume a new state feedback gain matrix k bar, right? So now the such that the control law is uk is equal to minus k bar x bar k, right? This is a new control law, right? And this control law places the closed loop poles to the desired location, right? That means this control law is also capable of placing the closed loop poles on the desired location, right? Now here this k is equal to, it is equal to k1 bar comma k2 bar dot dot dot, similarly up till kn bar. So these are the elements of this matrix K, right? Now because x bar is equal to t inverse x, because we assumed the new state here, okay, we assumed the new state here, this one. So from this we can get x bar is equal to t inverse x. So we will put it here, right? So uk will now be minus k inverse, sorry, k bar t inverse, right, and xk, right? So now this control law, this is also a control law, right? This is now updated control law. Now this control law will also place the poles of the original system. This control law will also place the closed loop poles of the original system, right? Original system to the desired location, right? To the desired location. Okay. So now, so if we see that all the poles and the given poles, the desired pole, these are the, let us say, desired poles, right? Okay, these are the desired poles. Okay, so these desired poles will give us a desired equation, characteristic equation, and that characteristic equation is given here. So we can simplify this characteristic equation to get this one. This is, let us say, some equation number 4, right? Now because uh, your pair A bar and B bar, these two matrices, they are in controllable companion form. Companion form. So we have this matrix here, right? So we can get this matrix. So we want that this k bar should place the closed loop poles of A minus B bar k bar in the desired location, right? Okay. So now let us see the characteristic equation of the original and canonical form. So if we see the characteristic equation of original, this is the characteristic equation of the original system, and this is the characteristic equation for the uh, canonical form, right? So if we solve this, we will get this one, right? Now the characteristic equation of the closed loop system, with if we take this as the control law, so the characteristic equation will be given by this equation here, right? So if we substitute, okay, so this can be obtained by taking the A bar minus B bar k bar matrix. So we'll take this matrix and we'll get this equation here, right? Now this is, let us, equation number 5. If we compare this equation 4 and 5, so if we compare these two equations 4 and 5, so equation number 4 is given on the last slide. This is the equation number 4 here. So here we have, this is the desired characteristic equation, Zn alpha 1 and all that, right? So if we compare equation 5 with equation 4, so we will get the values of all these elements of matrix K. And this is, for example, some equation 6. So that means to get the state feedback gain matrix, the actual state feedback gain matrix, we need to find out the transformation matrix T, and then we can multiply its inverse with the companion form gain matrix, and we will get this K, right? So there are the steps. If we have to summarize the whole in theory, whole concept in some steps. So first step here is that obtain UC, and UC is the controllability matrix. Then the second step you can say is we have to check the open loop characteristic equation, which is zi minus a is equal to 0. This is the open loop characteristic equation, right? Then after that, we have to check for the desired characteristic equation, right? So we have to see the desired characteristic equation. So desired characteristic equation is z minus z1, z minus z2 dot 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 z minus zn is equal to 0. So this is the desired characteristic equation. And then finally we have to you know so here we have to obtain UC, we have to obtain W. W can be obtained here. So we'll write open loop characteristic equation and find W, right? So using UC and W, obtain T, right? We have to obtain T, the transformation matrix. Then last step is find K using K is equal to K bar T inverse matrix, right? So by using this procedure, we can easily find out a state feedback controller for the given state space model, right? So it is very easy concept, very interesting concept, right? We can use this concept to design controller, state feedback controller for the real-time systems also, right? So now this is so your it for today's lecture, and thank you so much.